8 puzzle example. As you can see, the name of the file is just test/8puzzle by program, and here you can see few lines of the code, and this is our starting point. Now let's remember Python code, how it looks actually. Feel a little bit about this example. Let's open graphical implementation of this program, and I will show you again 8 puzzle. So here we have 8 cards. We need to move empty one in such a way that we can sort all cards starting from 1 to 8. Here I can run the code and you can see how it works. So this is artificial intelligence task because we are able to make a choice from several choices, and we need to do these choices in such a way so that we can solve our puzzle. In order to understand how it works, let's try to debug this code. And this is where your learning starts. So here we open test 8 puzzle. There is no graphical interface here in order to simplify this process of debugging. So basically we see here that the code is just 2 lines, most important 2 lines. Line number 5, here you see on the screen, it is where we describe our problem, we describe our variables, values. I will go a little bit later in more details about it. And later we can choose, once we have description of our problem, we can choose algorithm which we would like to use for state space siege. And for example, I will try to debug it by using breadth fast siege. Once we've done our sieging, we have solution, and we print the solution in console window so that we can see basic steps which we need to do in order to solve this puzzle. In order to run this code, we need to import only one model. You can see here in Python just we import siege, all required models for this example to run. So as you can see, the starting point for this code is pretty simple. Let's try to debug it. And in the process of debugging, we will learn actually how everything works and how you can implement and solve such kind of puzzles. Click your mouse on the line on which you want to create a breakpoint, like this one. And then click the right button of the mouse, involve contextual menu, and run this debug code. Once I am in debug mode, I can press F7 and go inside the model and see what's going on. So now in this line, as you can see, what I am doing, I am describing the problem. There is class in Python which is called 8puzzle. This class actually it is described in this library, in this model. And in order to create it, I need to put initial state of my variables. As we can see here, in order to solve this puzzle, I need 9 variables, which I put in one list. The first variable, for example, 2, means that in the top left corner of my board, there will be card with number 2. Next to it will be card with number 4. And the last card in the bottom right corner of my board will be card with 0, empty one, which I can move. So this is my initial state. For this problem, we can see that I need actually 9 variables. Okay, once we understood it, let's press F7 in order to go inside this class and to see what's going on inside. As you can see here, the description of the class, it is in the model siege py, and here it is the name of the class. Here is name of superclass, abstract class, which dictates for us what methods we need to implement in order to have a problem for siege algorithms to work, and constructor of the object of the type 8puzzle. It is this one. And here we can see that what we are doing, we creating 2 variables for each object of the class 8puzzle. The first one, it is our initial state from which we start to solve this puzzle. And the second one variable, it is state which describes the goal. And by default, this is description of the sorted cards, which we like to find solution in order to sort this card. So once we press it, we can see that we use these 2 variables in order to create object. And in order to do this, we call superclass method super. It means I call constructor from the superclass problem, and I create these two variables for this class, initial and goal. And that's it, nothing more. Once we have done, we have description of our problem. These two variables, initial state and my goal state. In order to lean a little bit more, you can go deep inside 8-puzzle problem and look which method you need to implement in working problem, so that all algorithms which you can later analyze, these algorithms will work if you implement these methods. Like, let's go through these methods, for example. Again, we have 8-puzzle class, which inherits methods, required method descriptions, actually these abstract methods which you need to implement later from your superclass problem. Here we already discussed our constructor, and then basic methods actually which you need to implement. One of them, it is action. It means that once you have a state, what is state? Again, I will remind you that the state, it is some combination of these cards. Always, if I move one card, I change the state of my object, of my board. In this case, for example, I have state like this one you see in front of you, and here I can have 3 actions in this state. So this method, which I have just shown you here, when you put the state, all these 9 variables, the position of the card, and this method will return all legal actions you can do. So it starts from all possible actions in this place, up, down, left, right. Then it checks from the state which from these 4 actions are legal. It depends on the state. As I shown you, for example, here, I have only 3 legal action, left, up, and down. So here, in this place, you just remove action right from these all actions, and you return possible actions. Another important method which you need to implement always when you describe your problem is the method result. And as you can see here, description of the method, it returns a new state once you put all state and action which you want to use. So you have your all state, you put description of the action, and the method result will return the new state, new combination of these cards. Another important method which is used always in these siege algorithms are goal test. And here you can see it's very simple implementation. It just checks if the state which you pass as argument to this method is a goal state. If it is, it returns true. If it is not, it returns false. The final method is important in our state space siege. It is heuristic function. It means this heuristic function h, it returns some numerical evaluation of your state. You give a node which describes state. You just give a node in your siege graph problem. You take this node state, and from this state evaluate how close it is to your goal. Here is very simple implementation. You can see that we can what we're doing in this particular case. For this heuristic function, we count how many cards are misplaced from their goal positions. So here we just counted how many of them are misplaced, and more are misplaced, the worst case we have. So by this, we have a heuristic function to evaluate our state of our problem. Definitely, when you debug, you can go through all these methods, look inside, and we will do this now, and you will see how it works, how we use these methods in order to implement artificial intelligent solving problem approach, which we call state space siege. So let's return to our original code. So once we created a problem, we can use many of available siege algorithms in order to solve this problem. And here, just it is an example of breadth-fast graph siege. We give our description of the problem and we return a solution if it exists. So now let's go inside this method and look what is inside and how it works. So let's do it. Press F7. We can see implementation of breadth-fast graph siege for our problem. As you can see, Once we implemented our problem with the framework, like 8-puzzle problem, we can use this code for any such problem. So let's try to analyze the code. As you can see, we take approach to this state space siege as navigation through the graph. In the graph, each node represents a state. We have implementation of the class node. We initiate this node with our initial state from our problem. So we have problem, which we pass as argument here. We take from this problem initial state. You can see here. Always you can drag your mouse pointer to this variable and you can see values. So we create the starting node from our siege. So maybe let's go inside of this node class. Press F7 and we can see that the node in our graph consists from several parameters, which you can see here. It is state, parent, action, path, cost, depth. And these parameters we can use. And actually, in this case, the most important, it is just the state. As parent, action, it is just null values for these parameters. So just you can code. If you can, you want to skip a line in your debugging mode, you just press F8 and you just run through this, and that's it. We have the node, initial node in our graph, which has a value of initial state from our problem. As you can see here, we immediately test maybe this node, it is a solution. It is a goal test. We use a method goal test in order to check if it is solution. We always, once we just take a new node, we immediately test for the goal test. Maybe we have solution and then we return the solution. Let's go just inside, press F7, go inside, you can see this method and it receives state, our initial position of our cards. And in this statement, it checks, is it state, our initial state in this case, is it a goal state? And it is not, so it will return false. As you can see, it returned false. It means it is not a goal test. So we continue our code in the next line. Now, here we create a query. It means we create a container in which we will put our all unexplored nodes. So here, dquare is special type container in Python in which we can put and take off objects from both ends of the query. So it's called dquare. It's useful container in order to implement this code. So as you can see here, we create this container, dquare. The name of this container is frontier, and we immediately put our node as the first object in this container. Always, if you have questions, it's strongly recommended to explore various type of variables in order to get this better feeling what's going on. So you can below here in this window, you can see all the variables that describes the state of your program, and you can explore here all these variables. For example, if I want to look what it is in the container frontier, we can go here, open this container, and we can see that in this case, we have one node from our graph with our initial values that represents the card positions on the board. So we have only one node in our container, in our frontier. Because this algorithm tries to avoid situation when we have loops in the graph, tries to avoid to check several times the same node, the same state. In order to avoid this problem, we create another container, which we call explored nodes. And the type of this container, it is set. So here we put all explored states. Once we check it, these states, and we check it that they are not solutions, we will put in this container explored. So in order to keep a track of all the states which already we check it. And this will help us to avoid to check them again. Press F8 in this case and go to the next line. We already know that we put in our container frontier the first node, our initial state. We created empty container explored states. And now we go to the loop, which tries to iterate our container frontier, and we iterate until we completely empty this container frontier. So let's try to do several iterations in order to see what's going on. So as a first step, you can see here now, we take off from the container, from the frontier, we pop left. It's the method to take our node from this container. So we take off, and we can see, once we have done this, that frontier contains no other objects. It's empty. We immediately, this node, we add to the another container, explore it node. Here, we add this node in order to mark that we already explored it. Now, and of course, we check it, and so we know that it is not our solution. So we add here. Okay, press F8, and now we know that in frontier there is no objects, it is empty, and in explore it we have one node, initial node, which we already checked that it is not a solution, so we put it here. If we need, we can check here nodes which we already explored. Now what we are doing, the next step, we take our node and look what immediately children follow from this node in our graph. So we call expand method, which returns all the nodes, all images that can follow from our current state. Our current state of the problem, it is in the variable node. Method expand implementation returns all the children, immediately children in the graph, and in this case it will be all the immediately states that follows from legal actions I can do on the board. So we iterate, here it is just iteration statement, over the children from our current node, and for each child, the child it is just the new next state, we check, maybe this child is already in explored state, we check that the child, it is not in the frontier, so the new child passes the statement, this check, then we check, maybe it is goal, maybe you already find solution, if not, and in this case it is not, if it is, we just return solution, if it is not, we put this child into the frontier. And you can see, because from our initial state we can have two legal actions. After the first iteration through this loop, we have now in our frontier two nodes, two childs, and in our explored states we have one node which we already checked. And we can see that we return to the initial statement of our loop, and we iterate again. We take the next node from our frontier, add it to explored node, take all the children from this node, check is it a solution, and if it is not, we append it to the frontier. And it goes on and on until it finds solutions or explores all the nodes in our graph. So once we implemented it, we found a solution, we can print solution in the console, and here you can see the solution.